Welcome to this module, and this is in continuation with our first module regarding understanding the op amps. The idea of this particular two modules is to summarize what are the parameters, characteristics of an operation amplifier, and here now we will see filters and oscillators, because we will be implementing this particular theory that we are understanding in this two modules into various circuits. So, let us see what we are learning in this particular module. To start with, we will start with filters. So, when you talk about filters, filters are what? They are circuits that are capable of passing certain signal and blocking another. So, what do you mean by passing certain signals? The band of frequencies that you want to pass, we can design a circuit that will allow to pass those band of frequencies, our desired band of frequencies, while blocking the undesired signals, right. So, this property of the filters is called frequency selectivity. Now, if you divide the filters, filters can be active filters and filter can be passive filters. So, what do you mean by passive filters? Passive filters are filters that use RC, that is resistor and capacitor, resistor and inductor, or all combinations of resistor, capacitor and inductor, all three combinations. While active components or active filters are the one that employs op amp in addition to resistors and capacitors. All right. Now, what are the advantages of active filters over passive filters? So, active filters can design or can be designed to provide gain and hence no attenuation as in case of passive filters. We have seen that in the earlier course. Same way, there is no loading problem and active filters are cost effective. What are the applications? Applications are, it is used in communication and signal processing circuits. They are also employed in a wide range of applications such as entertainment and medical electronics. Of course, there are lot of applications, that is why we have written etc. Now, four basic categories of active filters: low pass, high pass, band pass and band reject, right. And further we can also classify active filters into digital filters and analog filters. So, digital filters are implemented using a digital computer or special purpose digital hardware, while analog filters can be classified as either active or passive, implemented with R, L and C as well as op amps. So, we have then seen each of those filters which are low pass, high pass, band reject. So, let us see once again low pass filter. What are low pass filter? Low pass filter allows for easy passage of low frequency signals from source to load and difficult passage of high frequency signals. So, now if you see the circuit, actual response would be ideal response if you see on the right side and actual response is on the left side. So, when you see ideal response, right, is like a brick, like a brick wall, where actual response is little bit different than ideal response, and here one new definition comes into picture is called roll off rate, roll off rate, all right. So, a low pass filter is a filter that passes frequency from 0 hertz to critical frequency. What is critical frequency? Frequency at which we want to stop the or frequency until which we want to pass the signal in case of low pass filter. So, FC here is the frequency, cutoff frequency or critical frequency above which we do not want the signals to pass, and that is why you see that after FC in the left side graph actual response plot, you see that after FC the signal starts attenuating, right. Okay. What other bands we can see? We can see a pass band, right. Then here we see this is your bandwidth, this is your transition region, this is your response of single pole RC filter. Single pole is when there is one R and one C. Here you can see one R and one C, right. So, roll off rate is about minus 20 dB per decade and then there is a stop band, alright. So, the y axis is gain, x axis is your frequency, alright. Now, pass band, what is pass band? Pass band, this pass band is the range of frequencies that are allowed to pass through the filter with minimum attenuation. While transition region, you can see here transition region, it shows the area where the fall off occurs. Now, so from here after the pass band is over, the fall off starts, the attenuation starts, and this is your transition region. Then there is a stop band, right, is the range of frequency that have the most attenuation. Finally, there is a critical frequency Fc, right, also called cutoff frequency, as we have, as I have just described in the last slide, and it defines the end of pass band and normally specified the point where the response drops to minus 3 dB or 70.7% from the pass band response, right. So, that is your critical frequency Fc. Okay. Now, when you want to design a low pass filter, first order low pass filter, resistor comes at the starting and then there is a capacitor. So, signal pass to the resistor and capacitor in this particular fashion. So, if I have Xc, Xc is nothing but 1 by 2 pi Fc, right. So, in a low pass at normal frequency, what will happen? At low frequency your Xc, right, Xc would be very high and the capacitor circuit can be considered as an open circuit. So, here if you see in the center, right, this one, in this case if your frequency is low, your Xc can be considered as open circuit and all the frequency, this is low frequency, can pass and we can get at the output. If the frequency is high, right, then Xc would be considered very low, Xc would be low, right. If f is high, Xc would be low. If Xc is low, then Vo is small as compared to Vin, hence the gain and drop falls gradually as the frequency is increased. This is how the RC filter works, right. A lower frequency, the circuit allows the signals to pass. At higher frequency or the frequency above cutoff frequency, the circuit will stop the signal to pass through it. So, the bandwidth of an ideal low pass filter, Fc, right, is equal to, bandwidth is equal to Fc, whatever critical frequency we have or cutoff frequency we have, that is equal to your bandwidth. The critical frequency of a low pass filter occurs when Xc equals to R, right, and it can be calculated using Fc equals to 1 by 2 pi Rc. So, first order low pass filter, if I use active filter is when you use amplifier, you use op amp, right. Here we are using op amp, and as you can see op amp is just in a non inverting configuration and it is a unity amplifier, right. So, the first order low pass active filter consists of simple passive RC filter and a low frequency part to the input of non inverting operational amplifier. The amplifier is configured as voltage follower, unity gain, or what you call non inverting unity gain amplifier, right, where its DC gain is equal to 1, right, DC gain is equal to 1. The advantage of this particular configuration is that the op amp has high input impedance. We have seen op amp input impedance is extremely high. So, this prevents excessive loading of filters output, while its low output impedance prevents the filters cutoff frequency point from being affected by the changes in the frequency of the load, right. That is the advantage of using the operational amplifier as unity gain amplifier or voltage follower, right. We are refreshing again what we have been learning in the last course, and people who have not registered for my last course, they may see the videos and come up with the understanding about this particular course. So, for those people who have not attended my last course, we are repeating, kind of summarizing the concepts in just 2 modules, alright. So, if I use amplification, if I use amplifier here, right. So, the signal is applied to the non inverting configuration, non inverting terminal of the op amp. So, what is the gain? Gain is DC gain is 1 plus R2 by R1, 1 plus R2 by R1, right, and my voltage gain is nothing but V out by V in, which is AF by under root of 1 plus f c by f c f by f c whole square, right. It is easy to know. So, what happens here? What happens here? For a non-inverting amplifier circuit, the magnitude of voltage gain, right, is given as a function of feedback resistor by the input resistor. So, you have RC filter here at the input stage, and then you have a non-inverting amplifier. So, here you can amplify the gain, you see the gain or signal can be amplified with the whatever gain you have, and you can set the gain with the help of R2 and R1, with the help of R2 and R1, right. So, that is the advantage. For this configuration, that is low pass active filter, we can see that at low frequencies f is less than f c and V out by V in is given by A f. At the cutoff frequency where f equals to f c, V out by V in is given by 0.707 A f, while at a higher frequency where f is greater than f c, V out by V in is less than A f, right. This will be kind of opposite to the high pass filter, and we will see that, alright. And the magnitude of voltage gain here, if it is in dB, then 20 log 10 V out by V in, that is minus 3 dB equals 20 log 10 0.707 V out by V in, right. Now, if I talk about second order low pass filter, I have 2 R and 2 C, right, 2 R and 2 C. Here the gain again A V is 1 plus R2 by R1, which you can see here, while f c would be 1 by 2 pi under root of R3, R4, C1 and C2, right. So, in this case, if my R3 equals to R4 and C1 equals to C2, I will have f c equals to 1 by 2 pi under root of R square C square. So, it will be nothing but f c equals to 1 by 2 pi R c. So, the cascading from single pole to 2 pole filter, we can make it by cascading the R and C. So, if you keep on cascading, the number of filter poles can be increased by cascading. To obtain a filter with 3 poles, cascade a 2 pole with 1 pole filters and so on. So, this is a 3 pole filter, low pass filter. 1 pole will give you minus 20 dB per decade, right. So, 3 pole will give you about minus 60 dB per decade. Now, if I talk about high pass filter, what is the change? High pass filter, we have capacitor at the input and then it goes to the resistor. So, signal goes to capacitor and a resistor, right. In this one, the high pass filter will significantly attenuate or reject all frequencies below f c, correct, and passes all frequency above f c. So, here the plot would be that here there will be attenuation at the input, and then as the frequency reaches close to f c and above f c, it will start, the signal can pass through the high pass filter, right. This is ideal response for high pass filter, and again formula remains same, f c equals to 1 by 2 pi R c. So, if I want to design first order high pass filter, right, with operational amplifier, and operational amplifier is a unity gain amplifier, then here I can again design a high pass active filter with a non-inverting unity gain amplifier. Non-inverting because the signals are applied to the non-inverting terminal, unity gain amplifier we know the circuit, right. So, this is how we can create a non-inverting this is how we can create high pass active filter. Now, if I want to use amplification factor into the high pass filter, then what will I do? I will have the op amp in a amplifier configuration as an amplifier. So, here you can see the op amp is used as a non-inverting amplifier. So, here I can change the gain or amplify the signal based on the gain that I can adjust, right. So, whatever I want, I can adjust the gain, and how can I do that? By changing the value of R2 and R1, right, because the gain for non-inverting amplifier is 1 plus R2 by R1. The voltage gain here in this case would be AF into 1 f by fc divided by 1 plus f by fc whole square. But what is AF? AF is your pass band gain, f is the frequency of input signal and fc is the cutoff frequency in hertz or critical frequency. So, here if you see in case of low pass filter V out by V in was equal to AF, and V out by V in case of high frequency was less than AF, right. Here it is opposite. So, here V out by V in less than AF, V out by V in for f equals to Fc is 0.07 and f greater than Fc equals to AF. So, one more thing is that the active filter, the active high pass filter has a gain AF that increases from 0 hertz to low cutoff frequency, right, low frequency cutoff point, and then Fc at 20 dB per decade as the frequency increases. At Fc equals to Fc, the gain is nothing but 0.707 of AF, and then when f is greater than Fc, your gain would be nothing but equals to AF. So, band pass filter, when you talk about band pass filter, it has a high pass filter, amplification and a low pass filter. Now, we want to pass a certain band, right. We have seen low pass filter that will pass the low frequency band, high pass filter it will pass the high frequency signal, and then when we want to fabricate or design a band pass filter, it should be a combination of high pass and low pass filter with the amplification if it is an active filter. So, the principal characteristic of band pass filter or any filter for that matter is its ability to pass frequency relatively unattenuated over a specified band or a spread of frequencies called pass band, right. The cutoff frequency or corner frequency of low pass filter is higher than the cutoff frequency of the high pass filter, right, and the difference between the frequencies at minus 3 dB point will determine the bandwidth of the band pass filter. So, it is very easy to understand low pass filter and high pass filter. So, now if you see here, if you want to fabricate or if you want to design a circuit, right, which is band pass filter and that too is passive, then you can use a combination of high pass filter and low pass filter. You see the signal from high pass filter, the signal from low pass filter. So, if you combine both, you will get a band pass filter. So, cascading together the individual low pass and high pass filter produces a low Q factor type filter which has a wide pass band. This is just a simulation. If you want to work on the simulation, you can use Simulink, right. Then band reject filter. So, as the name suggests, it will reject a particular band of frequencies, right. So, the figure shows which figure here it shows, right, the stop band, pass band and pass band. So, it shows the ideal frequency response of band stop filter. This is a band stop filter, it is also called band reject filter, right. You can see here this is the band stop or band reject filter, or it is also called notch filter, alright. So, do not get confused if it is band stop or band reject or notch, everything is same. So, band stop filter is formed by combination of low pass and high pass filters with a parallel connection instead of cascading connection, right. In the case of band pass filter, we were cascading low pass and high pass. In case of band reject filter, we are again cascading, but in a parallel configuration. The name itself suggests that it will stop a particular band of frequencies, right. Since it eliminates frequency, also called band elimination filter or band reject filter or notch filter, right. So, we know that unlike high pass and low pass, band pass and band stop filters have two cutoff frequency. You can see here FL and FH, right, two cutoff frequency. It will pass above and below a particular range of frequency whose cutoff frequencies are predetermined depending on the value of components used in the circuit design, right. By changing the value of R and C, we can change the value of FL and FH, right, or we can pass certain band of frequency, we can reject certain band of frequency, alright. Now, any frequency between these two frequencies are attenuated, it has two pass bands and one stop band as you can see from the figure. So, band reject filter, right, it has a RC low pass filter that can combine with a RC high pass filter. Now, we can also combine these RC filters from another type of filter that can block or severely attenuate a given band of frequencies between two cutoff frequencies and pass all the other frequencies, right. So, by tweaking the values of R and C, we can just allow a certain band of frequency to pass or even a single frequency to just block, alright. So, only single frequency to attenuate or band of frequency to attenuate. So, if it is just a small frequency or very low range of frequency or very small range of frequency, while it can pass all the other frequency, then it is called notch filter, right. So, if this stop band is very narrow, you can see this stop band is here, right, and if the stop band is extremely narrow, that means only a certain frequencies are stopped, only small range of frequencies are stopped, then it will work as a notch filter, right, because the frequencies response, when you see this response, it will show like a notch. So, deep notch with high selectivity. A typical band reject filter frequency response is shown here, you can see here. Now, if I want to design the band reject filter, then this is the circuit that is used for designing. There is a low pass filter, high pass filter in a parallel configuration, and then there is a summing amplifier, right. So, how does it work? So, the transformation of these filter characteristics can be easily implemented using a low pass and high pass filter isolated from each other by non inverting voltage follower, right. See, voltage follower is here, it is here, right. The use of op amp within the band stop filter design also allows us to introduce voltage gain into the basic filter. Then the two non inverting voltage followers can easily be converted into basic non inverting amplifier with a gain of AV equals to 1 plus RF by Rn. This non inverting voltage follower here or unity gain amplifier can be converted to an amplifier by changing the RF by Rin, right. We can connect RF and Rin. Thus, if we require a stop band filter to have its minus 3 dB cutoff, say at 1 kilohertz and 10 kilohertz, and a stop band gain of minus 10 dB in between, we can easily design a low pass and high pass filter with these basic requirements, right. Then we have seen oscillators. So, when we talk about oscillators, we have seen Bark-Hussein criteria, and what does Bark-Hussein criteria says? Bark-Hussein criteria says that, let us see, 1, what does it say? 1 is that the phase, the output signal that is sent back to the input, the feedback signal, right, should be in phase with respect to input signal, right. So, the phase shift, right, of the output signal compared to input signal or the feedback signal compared to input signal should be 0 or 360 degree phase. Second, it says that the mode of A into beta should be greater than equal to 1, 2 criteria. Okay. So, first is that the oscillators, when you want to design a operational amplifier in as an oscillator, then you have to apply a positive feedback, right. And as you can see here, right, that there is a signal Vs, there is an input signal Vi, this input signal Vi depends on Vs and the feedback signal Vf. There is an amplifier which amplifies the signal, and the output, the part of the output signal is feedback to the input, and what I said is that the part of the output signal that is fed back to the input should have same phase with respect to the input signal, alright. So, let us see, you can see here that only a part of output signal is feedback. If I increase the beta, if I increase the feedback, what I have? I have AF extremely high, and in case of 0.05 for a gain of 20, I see that the feedback gain is infinite, right. Thus we had to follow a Bark-Hussein criteria, and you have to understand that only a part of the signal is fed back to the input. We have seen this thing in earlier course, I am just quickly repeating it here, so that you understand, because we will be using this for actual implementation of circuits, alright. So, you can see that the feedback must be positive, voltage derived from output using feedback network must be in phase with Vi, right. Thus, if I use an inverting amplifier, as you can see here, right, you can see the signal here and signal here is 180 degree phase shift compared to the input signal, correct. So, if I want to feedback, if I want to feed this particular output voltage through the feedback network back to the input, then the feedback network should introduce another 180 degree phase shift, right, because you see 0, 180, 180 is fed here. If I want to make it 0 or 360, another 180 degree phase shift I will implement in the feedback network, right. So, feedback should be having 360 degree phase shift or 0 degree phase shift. Right. Another point that we discuss is mode of A beta should be equal to 1 or greater than equal to 1, because initially you want to start the oscillator, then mode of A beta should be greater than 1 and then you can make it equal to 1. All right. So, this is very important criteria you have to understand, and you have to design a circuit that can follow this criteria, otherwise the oscillations would not happen. All right. So, what are these states? We have already discussed. First is the total phase shift around a loop as the signal process from input through our amplifier feedback network back to the input, completing a loop is precisely 0 or 360 degree. And second is the magnitude of product of open loop gain and feedback factor beta should be 1. All right. So, what happens if it is greater than 1? What happens if it is equal to 1, and what happens if it is less than 1? What? A into beta. A is gain, beta is feedback. So, when the total phase shift around a loop is 0 degree or 360 degree and A beta is greater than 1, then the output oscillates, but the oscillations are growing type. You can see the oscillations are growing in nature, right. But when you talk about A beta equal to 1, then you will see that the total phase shift around phase shift is 0 or 360 degree. This is still we have to maintain this condition, but if I have A beta equal to 1, then the oscillations are with constant frequency and they are called sustained oscillations. Oscillations are sustaining, right. But if I have A beta less than 1, A beta less than 1, then what will happen? Then the total phase shift around the loop is 0 degree 360 degree. See, every time we have to write this sentence, phase shift should be 0 degree or 360 degree, but if I have A beta less than 1, then I will see a damping type of oscillation, right, or we can say decaying. The oscillations are decaying. All right. Now, the question comes that how oscillator starts, because is A beta, right, is kept at higher than unity, and then the circuit adjusts itself to A beta equals to 1 to result sustained oscillations, it is okay. But the obvious question here is that if no input signal is required, here we say that, right, in oscillator there is no input signal required. If input signal is not required, then how the oscillator starts and from where does the starting voltage come? So, we can see that the starting voltage comes because of the free electron, because every resistance has a free electron, and under influence of a normal room temperature these free electrons move randomly into various directions, right. Such electrons will form a voltage called noise voltage, and these noise voltage are amplified. Hence, to amplify such a small noise voltages, we need to keep A beta or mode of A beta is slightly greater than 1 or slightly greater than unity, right. Then once we have these oscillations, we can keep A beta equal to 1 and phase shift 360 degree to have a sustained oscillations, right. This is the starting of the oscillator. Now, if you want to talk about oscillators, oscillators are classified into several categories based on output waveform, based on circuit components, based on range of operating frequency, and based on whether feedback is used or not. These are 4 different components, there are 4 different classification of the oscillators, right, and we have seen this. Let us see once again. Classified as sinusoidal, non-sinusoidal. Sinusoidal oscillators produces sinusoidal waveform, but non-sinusoidal produces square wave, triangle wave, etc. Same way, based on circuit components, whether we are using R, C, L, LC, right. So, if it is R and C, it is a RC oscillator, if it is L and C, it is a different kind of oscillator. We will see different kind of oscillator depending on how many L, how many C, it can be Hartley oscillator, it can be Colpitts oscillator, right. So, we have to understand that depending on the circuit components, we can also classify oscillator. Depending on waveform, we can classify oscillators, sinusoidal waveform or non-sinusoidal waveform. Then based on operating frequency, where low operating frequency, audio frequency, or it is a higher frequency, right. So, if it is RC oscillator, it uses low frequency, if it is LC oscillator, it uses higher frequency, right. So, based on frequency, we can classify the oscillator. Then we have based on whether feedback is used or not. If feedback is used, it is called feedback type of oscillator. Feedback is not used, non-feedback type of oscillators, right. So, we have different classification of oscillators. If you see the screen, the non-feedback type of oscillators uses the negative resistance region of characteristics, and this is a UJT relaxation type oscillator. So, UJT relaxation type oscillator is your non-feedback type oscillator. So, if we discussed phase shift oscillators or RC phase shift oscillators, then it is in this particular configuration. You can see C and R. Now, if I work on the circuit, and I solve this circuit, right, what will I have? Let Vi equals to Vm sin omega t, if this is the input, right, and impedance of it is Z equals to R minus j x c, where x is nothing but 1 by 2 pi f c into z, and the mode of z should be less than your theta or phi. So, if I solve this, then what will I have? I will have I equals to this particular equation, right, mode of I angle plus phi degree into A. The positive phase angle indicates the current leads applied voltage. You can see here there is a positive phase angle, right, and this positive phase angle, what does it says? It says that the current leads applied voltage by angle phi, and now VO equals to IR. So, as the output voltage VO is dropped across the resistance and it is in phase with the current, hence the output voltage leads the input voltage by angle phi, correct. Output voltage leads by angle phi. In general, phi is called phase angle of the circuit and depends on the value of R and C. When the value of C is very large as compared to R, then the phase tends to be 60 degree. So, for a single C and R, if the value of C is higher, then we can get a phase shift of 90 degree, but in practice these values are so selected that phase shift is 60 degree, right. So, if your C is high, right, compared to R, then we have a phase angle of or phase shift of 90 degree, but we have to adjust R and C such that we have a phase shift of 60 degree. Why? Because these RC circuits are used in the feedback, So, if I have a feedback, that means that each RC producing 60 degree, 3 RC will produce 180 degree, right. So, if I have a phase shift of 180 degree at the output compared to the input signal, then if I feed this output back to this RC circuit, I will have another 180 degree phase shift. So, my total phase shift is 360 degree or 0 degree, which will satisfy my Bar-Coushain criteria, right. That is the use of RC. So, you can see here, if the signal is applied to the inverting terminal, right, I have a 180 degree phase shift at the output. I am feeding it to the RC feedback circuit, and I will have another 180 degree. So, 180 plus 180 will be 360 degree, and some part of the signal is fed back to the input to sustain the oscillations, right. We have seen this. We have also derived the equation for the gain and equation for the beta, right, and what we found is that beta in case of RC phase shift oscillator should be 1 by 29, while gain should be greater than 29, right. So, you please see my earlier lectures, right, in another course. The course name is integrated circuits, MOSFETs, op amps and their applications. If you see YouTube videos, you will find how we are deriving these equations such as gain, equations such as feedback network or feedback component beta. So, for RC phase shift oscillator, we have beta equals to 1 by 29, while gain equals to 29. So, if you come back to the screen, what we see, if we have beta equals to 1 by 29 and gain is greater than equal to 1 by 20 greater than equal to 29, then mode of A into beta would be greater than equal to 1, and I have a phase shift of 0 degree or 360 degree. Thus, I am satisfying the Bar-Cosen criteria. Thus, to have the oscillations, the gain of op amp must be equal to or greater than 29, which can be adjusted by changing the feedback and input resistance. Now, let us see another oscillator, which is Wien bridge oscillator, alright, and in Wien bridge oscillator there is no phase shift is not there. So, Wien bridge oscillator is an audio frequency sine wave oscillator of a high stability and simplicity. It has two RC amplifier circuit connected in Wheatstone. You can see here RC here, RC here, right, one is in series, another is parallel, right. The basic circuit is shown in figure. The output amplifier is amplified between terminal 1 and 3, right. The output of amplifier is feedback between terminal 1 and terminal 3, right. The amplifier input is applied between terminal 2 and 4, right. The resistor value are adjusted such that the input to the amplifier must not be 0 or non-vanishing, right. The RC network is responsible for determining the frequency of oscillator. RC network, which is here and here, it determines the frequency of the oscillator. So, here how many RC oscillators? Here there are 2 RC oscillators, right, one series R1C1, another parallel R2C2, right, and these are called frequency sensitive arms. So, if we consider just feedback, then R1C1, R2C2 in this particular configuration, I will say R1C1 as Z1, R2C2 as Z2, right. I am applying input between 1 and 3. So, V in our output is between 2 and 4, right, or sorry 2 and 1 and let us see what is that 1 and 3 is the output feedback from the amplifier, and between 2 and 4 my feedback is there, right. So, solving this particular equation, solving this, what we get? We get f equals to 1 by 2 pi RC. The frequency formula for this oscillator is 1 by 2 pi R1 under root of R1 R2 C1 C2. But when R1 equals to R2 and C1 equals to C2, we have 1 by 2 pi under root of R square C square is nothing but 1 by 2 pi RC, right. So, my beta, which is the feedback network, here in this case, if I solve further, what is that? Beta is nothing but 1 by 3, right, and what is my gain? My gain should be greater than equal to 3, then only my A into beta would be greater than equal to 1, because 1 by 3 into 3 is greater than equal to 1, right. So, this is required gain of the amplifier without any phase shift, because there is no phase shift in case of Wien bridge oscillator, alright. In case of Wien bridge oscillator, there is no phase shift. But what if R1 is not equal to R2 and C1 is not equal to C2, then we cannot have f equal to 1 by 2 pi RC, right. In this case, we will have, if on substitution, we will have C1 R2 VO by VI, right, beta is VO by VI. So, I have this formula, and then my A gain would be based on this particular equation, alright. But the advantage of Wien bridge oscillator, right, is that by varying the capacitor simultaneously, right, by varying the two capacitor values simultaneously, we can have different frequency ranges. This is the advantage of Wien bridge oscillator. Second is there is no phase shift required in the feedback network, right. That is the second advantage of the Wien bridge oscillator, right. So, if the amplifier, you see, if the Wien bridge oscillator is used with an operational amplifier, right, in this particular configuration, right, then what will happen? The resistance and capacitors are the component of frequency sensitive arms. You can see here the resistance RF and R1 are part of feedback network, right, RF and RF, and R1 would be part of the feedback network for the amplifier, and gain would be, because signal is provided at the non inverting terminal, gain would be 1 plus RF by R1, right. According to oscillations for Wien bridge oscillator, A should be greater than equal to 3, that means 1 plus RF by R1 equal to greater than equal to 3, or RF by R1 should be greater than equal to 2. So, we can adjust the value of RF R1 such that my value comes greater than or equal to 2, right. So, for the oscillation to occur, the frequency calculated is f equals to 1 by 2 pi RC. Feedback is given to the non inverting terminal of the op amp to ensure the 0 phase shift, right. Frequency feedback is given to the non inverting terminal, you can see here, so that we have a 0 phase shift at the output, right. So, this is about this particular module, and we have seen how the oscillators can be designed, as well as we have also seen how the filters can be designed, right. In the next module, which is the last module for the summary, so that we understand how we can implement these things in the practical applications, right. We will be looking at few other oscillators, that are LC oscillators, and we will see that how we can change the inductors and capacitor, the value of inductor and value of capacitor to obtain the LC oscillators. LC oscillators, as we have discussed, are used for high frequency applications, and RC oscillators are used for low frequency applications, right. So, let us see in the next class how we can design LC oscillators, and that will be the last module for this particular lecture, all right. So, I will see you next class. Just go through this and refresh your understanding about op amps and its application. Then we have to actually implement those op amps for different applications, all right. I will see you in next class. Till then, you take care. Bye.